Welcome, data managers, to part 3 of the permutations videos. This is the final video for permutations. So up to this point we've learned about factorial notation, we've learned about permutation notation and PR, and now we're going to do a quick review of some of the concepts that we've learned so far in this particular learning activity. So first of all, we've got factorial notation. When you arrange all of your objects, you can use factorial notation as the shortcut. And the simplest example, n factorial. So if you've got 10 people in a line at a grocery store, so that's 10 people in a line, there are 10 factorial ways of arranging those people. That's a lot of ways of arranging people. The second concept is permutation notation. So in this case, it's when you're arranging only some of the objects from that whole collection. So in this case, you're using permutation notation as the shortcut, NPR, or N arrange R. So how many ways can you arrange R objects from N objects? Now let's take a look at the example. You've got 100 people entered into a race. How many different ways can you have first, second, and third place be decided, assuming that every single person has a chance of achieving those? Well, in this case, it's 100 PR, or 100 arrange 3 objects. And in this case, it's going to be 100 times 99 times 98. And you ought to know by now as well that you can use the factorial notation, n factorial over n minus r factorial. So in this case, it would be 100 factorial divided by 100 minus 3 factorial, so divided by 97 factorial. By the way, it's much easier for your calculator to handle 100 times 99 times 98 than to punch 100 factorial in. Chances are it'll crash. Another concept you need to be cognizant of are the restrictions. Always deal with them first, identify them, figure out what they mean. So for example, you still have 10 people waiting in line at a grocery store. How many arrangements are there if you put the oldest person at the front? Well, that means you just eliminated one person out of the 10. So that one person, you can only arrange that person in one way. That means you only have 9 people to arrange. So the answer in this case would be 9 factorial, or 1 factorial times 9 factorial. Let's add an additional restriction. Let's put the youngest person at the back. So the oldest at the front, the youngest at the back. In this case, you fix the position of 2 of the people, and you end up with 3 blocks effectively. Remember those blocks ideas? And you'll see them again next. So anyway, that means you're only able to arrange 8 of the people. So in this case, we've got an answer of 8 factorial. Now, I just mentioned blocking objects. Well, you're grouping objects. Now, if you need objects to stay together, it's easier to think of them as a single object or a block. But there are 2 questions you need to ask yourself. First of all, do you arrange inside the block? In which case you've got another factorial to worry about. And do you need to include the block as one of the objects to be arranged? So is the block fixed in a particular spot, or does it get to move around like all the other objects? So, for example, a family of 6 going to a basketball game. Well, how many ways can that family sit in a single row at the game, assuming there are 6 seats side by side? Well, surprisingly, there are a lot of ways, 6 factorial, or in this case 720 different ways. But let's restrict that. So now that the oldest has to be in the 3rd seat and the youngest has to be in the 5th seat, because, well, the youngest happens to pester the oldest and the oldest responds. So you need to keep them separated. So you've restricted yourself. So in this case, you can take a look at how this would be laid out. You've got 4 possibilities for the first seat, 3 for the second seat. There's only 1 possibility for that 3rd seat, but you've got 2 possibilities for the 4th. There's only 1 possibility for the 5th, and then you're also left with 1 possibility for the 6th. So in this case, you're dealing with 4 factorial. Now, assuming the parents sit together, how many do you have in that case? Well, the parents behave as a block, so they're one of the objects. But the parents themselves can sit on either side of each other. So they may be in a block, It may be one object out of 6, but that object still has different possible permutations. So in this case, you've got 5 different objects, effectively, but the one object has 2 possibilities. So it's 5 factorial times 2 factorial. And then finally, what happens if the parents must sit together next to an aisle? Well, you fix the parents, but the parents still haven't been told in which seat to sit. So in this case, you've got 4 possibilities, because the parents aren't part of the possible movement of the children. 4 factorial times 2 factorial. Another concept you should be familiar with is indirect reasoning, and that's where solving a problem directly is too complicated. So in this case, you want to do the shortcut of taking all permutations and subtracting those permutations you don't want to get those that you do want. Because oftentimes it's quite easy to find all possible permutations, and you can also sometimes figure out which ones you don't want, and the remainder are the ones you do want. So let's use the example of the basketball game in the family of 6. Now in this case, our restriction will be how many ways can the parents sit apart? So if we were to do it directly, we would end up with a very messy solution. It would take forever and ever and ever and ever. So instead, we're going to figure out how many permutations there are total, and then we're going to subtract the number of permutations where the parents sit together. It's easy to do together because the parents sit together as a block, as a single unit, and they behave as a single unit. Whereas if you sit them apart, you end up with a very messy situation. So, first of all, how many permutations do we have if we have all options? 6 factorial, 720. And then we have to take a look at the number of permutations where the parents sit together. So in this case, we already figured out that it would be 5 factorial times 2 factorial. 5 factorial, 4 children and 1 parent block. So there's 5 blocks kicking around. And within the parent block, the parents can sit in 2 different ways. So that's the 2 factorial. So in the end, we end up with 480. I suggest you take a moment to pause here and to think about this particular problem. So there is a special restriction that deals with digits. So when you are writing a 4-digit number, 0, 1, 2, 3, this would be perfectly acceptable if you were to choose a 4-digit PIN. And they would behave as if they were letters. You could just as easily insert letters. You could put anything in there, as long as there was some variation. However, if you treat it as a number that you are using in a mathematical operation, that initial 0 has no meaning. So you would have to assume that 1, 2, 3 is a 3-digit number, not a 4-digit number. So in that case, there is a restriction. The first digit can never be a 0. That's provided you've got a number greater than 1. So let's take a look at that. How many 6-digit numbers can be made if no digit may be repeated? So for example, 1, 2, 3, 1, 4, 5 is not valid because we've repeated number 1. So we've got 6-digit numbers, and no digit may be repeated. Take a moment to think about that. So let's lay it out for you. 6 digits. 1, 2, 3, 4, 5, 6 digits. Now, we know that the first digit cannot be a 0. That means we have only 9 possibilities for the first number. Now, the second number, it doesn't matter whether 0 is in there or not, it's allowed. But we've already used one number. So again, we've reduced our total number of possibilities to 9. And then each time we use up a number, 8, 7, 6, 5, and so on. Well, in this case, we only go down to 5 because we have 6 digits that we're working with. Now, let's think about how we could use permutation notation here. Well, let's ignore this first digit for now. That confuses things. Second digit, we've got 9, 8, 7, 6, 5. This reminds me so much of permutation notation, where we start with 9 possibilities, and we're arranging 5 of them. We got 1, 2, 3, 4, 5. So this in this case it would be 9 arrange 5. So we're dealing with 9p5. Now, however, we also have our first digit. So in this case, we have 9 possibilities for our first digit multiplied by all the arrangements, all the permutations that come after it. So we have the multiplication sign, 9. So in this case, we would be doing 9 times 9 arrange 5. So, as you were warned, digit questions are typically a little bit tricky because there are restrictions which are implied rather than stated. So, let's take a look at this question. How many 7-digit odd numbers are there with no repeated digits? So just to give you a heads up, the first digit obviously can't be a 0, we've established that, and you're also going to have to think about how we deal with the last digit. So, 7-digit odd numbers. Let's see how we solve this one. There are 2 restrictions here. The first is that we are always dealing with odd numbers. That means the last digit can only be 1, 3, 5, 7, or 9. And the other restriction is that our number cannot start with a 0. So how do we approach this question? Well, I recommend in this case that you first look at the 5 choices for the digit in the last number and use that first. So in this case, we've got 5 as our limiting factor. Now, so that means we take out 1 possibility already. We also have 0 eliminated for the first option. So 5 takes out 1 possibility from 10 to bring it down to 9. 0 takes out another possibility to bring it down to 8. So we start off with 8 for our first digit, 8 options. The second digit, once again, we can introduce 0 again, so that even though you would normally reduce it by 1, we can also increase it by 1 this time. So 8 times 8. And at this point, you start going into a regular permutation. 8 times 7 times 6 times 5 times 4. So to solve it algebraically, you would have 8 for the first digit times the permutation whereby you arrange 5 objects from 8 times the number of odd numbers. So let's try something even more pesky. Finding the number of even numbers where you don't repeat the digits. Why is it more complicated? And how many 6-digit even numbers can there be with no repeated digits? So let's take a look at what's going on here. So for the even number, we only have 5 possible endings, 0, 2, 4, 6, 8. But the problem is, one of these numbers will change the number of choices that we have for the first digit. So let's take a look at our 5 cases, our 5 scenarios. So if the number ends in a 0, we have the first number is a 0, and what it doesn't do is reduce our initial number over here. Because you remember in previous cases, we always reduced our number from 10 to 9. Because we weren't allowed to have a 0 in the first place. But in this case, we've already used up our 0, so we don't have to worry about that, so it's still 9. So in this case, if we use 0 as our even number, we have 9 times 8 times 7 times 6 times 5, and then times 1 for the 0. So in this case, we would be doing 9p5 times 1 factorial for the 0. It gives us 15,120 options. Now, if we do not use the 0, we've got a different story going on. So if we use 2, so that eliminates 2 from any other position. So 2 is our last digit. That means our first digit here still has the 0 restriction, so we can't use that, reduced to 9, and 2 reduces it to 8. So in this case, we've got 8. And then our second digit, we have already reduced the total number of options by 1. 0 is allowed again, which is why we're back at 8. So then we've got 8 times 7 times 6 times 5 times 1. So in this case, we've got 8 times 8p4 times 1. Or sorry, my apologies, that would be 1 times 8p4 times 1. I have a feeling I made a mistake earlier. And when we figure out how many possibilities there are 13,440. Now if we do that for 4, 6, 8, and 10, we end up with the same result. So 2, 4, 6, 8, that gives us 4 other cases. So 4 times 13,440 plus 1 times 15,120 should give us our total. Now, there is another way of doing this. We can look at 2 cases. So by looking at only 2 cases, we can simplify our solution considerably. So either the even number ends in a 0, or it ends in 2, 4, 6, 8. So in this case, we first compute the total number of possibilities if we end in a 0, and then, rather than doing 4 times a separate calculation, it behooves us to remember that 2, 4, 6, and 8, they occupy a single position. That means 4 possibilities. So in this case, we have a different solution. So we still have the 8 times 7 times 6 times 5, but rather than multiplying by 1, we're multiplying by 4, because we just stuck the 2, 4, 6, and 8 all together. So when we do this math, we end up with 68,000 even 6-digit numbers where no digit is repeated. Finally, the third possibility is to use the indirect reasoning solution. So in this case, we're going to look at all arrangements where there were no digits repeated, and then we're going to subtract the odd numbers where there were no digits repeated. Because if we get rid of odd numbers, that leaves us with only even numbers. Remember the complement idea? So the odd numbers would be the complement to the even numbers. So in this case, we're going to do our arrangement of no repeated digits, 9 times 9 times 8 times 7 times 6 times 5, and we're going to subtract what we figured out for the odd numbers with no repeated digits. And again, we end up with the same solution. Very handy. So that means there are 3 different ways to solve for this problem. They're obviously different. They're obviously each tricky, but in the end, once you practice it and once you master it, they can prove very useful. This goes way beyond this course in terms of usefulness. That's it for permutations. I strongly encourage you to do the Explore Learning gizmo that relates to permutations and combinations. Now the thing is, you should know that it works far better in Firefox or Internet Explorer, and quite probably in Safari as well, than it does in Google Chrome. So it's unfortunate. I use Google Chrome for everything, but I had to switch to Internet Explorer to complete that particular activity. So if you have questions, please make sure to email me, and otherwise keep working.